It is 5:18:17. 1 part is the solvent, 1 part is the solute, which is which? Okay, so the thing being dissolved is the solute, which leaves the solvent as, well, it's a little hard to point to, the water. And I've tried to represent those water molecules or water particles with little green dot or little blue dots. If we are at a point where particles are leaving the solute solid state, they are dissolving at the same rate that they are recrystallizing. They are re-entering a solid state. What do we call that condition? Equilibrium. Yeah, so that would be solution equilibrium. Things are recrystallizing and dissolving at the same rate. Opposing changes happening at the same rate. Just like Le Chatelier and phase change equilibrium, this is solution equilibrium. All right, now, we said that a couple of things cause the rate of dissolution to increase. Name them. 3 things you can do to get your solute to dissolve faster. Heat it up. Stir it. Beat it. Alfred Hitchcock it. So basically, changing the particle size of the solute will also increase the rate of dissolution. Now, that said, there are upper limits to solubility. And all substances have a given solubility in all solvents, though we most often talk about water. Water is sometimes called the universal solvent because it's a really good solvent. It dissolves a lot of things. It's a polar compound. It's got other kinds of things going for it, but it's great at dissolving things. So for every substance that we know of, we have given solubilities. And what I've got here is a solubility table. And this is the solubility of various compounds in grams per 100 grams of water. So note that we're using a mass of water as well as a mass of the solute. And this is just a small sampling. We've got ammonium iodide through ammonium selenate. And what do you notice? I'm going to give you a copy of this. What trends do you see? Give me one trend. Okay, so the amount of solute in grams that you can dissolve in 100 grams of water for all of these increases as the temperature increases. What else do you notice? Anything? What do you notice about the compounds we're looking at here? They're all ionic? Yeah, we'll go with that. They're all ionic compounds. Remember that from looking at ionic versus covalent compounds, ionic compounds tend to be highly water soluble. Water has those regions of partial charge. It's a polar compound. Polar compounds dissolve ionic substances readily. Now, let's get back to those words saturated, unsaturated, supersaturated. Okay, an unsaturated solution. What is that? It has not dissolved all of the solute that it can. It can take more. It can dissolve more solute. What about a saturated solution? Okay, it has as much solute as can possibly be dissolved in it. You cannot get anything else to dissolve in it. If you add more stuff to it, it's not going to dissolve. It's going to sit in the bottom. So, full of solute. Can't dissolve anymore. Then what is a supersaturated solution? Yeah, it's actually holding more solute than you would expect it to be able to under those temperature conditions, and typically the way we get this is to heat it up, add more solute, and then cool it. And if we can get it to do that without stuff coming out of solution, what we have is a supersaturated solution. When you guys made your solutions of alum, ammonium chloride, which you did for, what was that, like 3.5 years you worked on those? Yeah, we wasted a lot of time on alum crystals, unfortunately. You kept heating it up and adding more in order to get a supersaturated solution. Now, did you have any luck with having nothing come out of solution? No, you all got crystals eventually. Some of them were tiny, they were all on the rims of the jars, they weren't where they were supposed to be, and they didn't grow big and fat like we expected, but we got crystals. Once you start to have that stuff come out of solution and crystallize, you no longer are looking at a supersaturated solution. You're now looking at a saturated solution with crystal chunks in it. Okay, that said, let's look at this, and let's practice using the solubility table. We'll do the first one on your practice sheet together. If you want to create a saturated solution of ammonium nitrate at 20 degrees Celsius using 550 milliliters of water, what mass of solute would be required? I'm going to start off by finding ammonium nitrate, and that's right here. And I'm going to find the mass of ammonium nitrate that I should be able to dissolve in 100 grams of water, right there. And it's 192 grams of ammonium nitrate. Ammonium nitrate is incredibly soluble in water. Nitrates tend to be very soluble, and ammonium nitrate is, and as do ammonium compounds, so ammonium nitrate is like super soluble. Okay, now we have one slight problem. This chart gives us solubility in 100 grams of water. Do we typically measure water by mass? How do we typically measure water? By volume. Yeah, liters, milliliters. Is there any known relationship between the mass and the volume of water? What is it? You guys don't even get the musical clue, do you? 1 is the loneliest number. 1 gram of what? 1 is the loneliest number was the musical reference. Where was I? So, anyway, 1 milliliter of water has a mass of 1 gram. Well, that's convenient. So, what do we start off with? We're going to do this as a factor label. So we know that we're going to start off with a given, and our given here is 550 milliliters of water. And our chart gives solubility in grams of water, so what we have to do is say that 1 milliliter of water is equal to 1 gram of water. That's a good start. Now, here are a couple tips and tricks that I typically use so that I don't screw up and do something stupid. You're looking at everything through the lens of 100 grams of water, but then I put in, again, for myself, so that I don't screw up, at 20 Celsius. And that's a visual cue to me to remember to go back and look at my solubility. And what I know is that 100 grams of water at 20 Celsius can dissolve 192 grams of ammonium nitrate, NH4NO3. So I'm going to do the factor label, do the math. Let's get a raw number. If you have a raw answer, something like this, 1,056 grams of ammonium nitrate. And we can have 4 sig figs, so that's what we need. Pretty easy. So what I'm going to do is turn you loose to work on the rest of these on your own. In a couple cases, let's just look real quickly at this. In a couple cases, we're asking about the mass of the water, and it's the same relationship. What you're using as your conversion factor is the mass of solute that can be dissolved in 100 grams of water. That's kind of like the mole ratio for these. That's the relationship that you're looking at. Okay? So I'm going to turn you loose. I'm going to float around, and we'll come back to it. Okay, so continue problem solving. Continue to look for that ratio of mass of solute to mass of water, and remember to check your temperatures. That's it.